We just look upon the two-terminal device that is PN junction diode. So we see the how the current flows through a PN junction diode when different type of voltages are applied to it. That is the bias voltage and reverse bias voltage. Also, we see how we can write the script for a device configuration of a PN junction diode. So in today's class, I'll just discuss the leftover part, that how to construct a PN junction diode in SDE. Instead of writing a script, if you want to construct a device, how you can do it, that is the first part. In the later part of the experiment, we have left over with the device, how a device physics behaves inside a PN junction diode. That is how a energy band diagram changes with the application of different voltages, how the electrostatic potential and barrier potential varies inside a diode with different voltages. So this will cover our half of the lab portion today. In the later part of the experiment, we'll deal with the single terminal device, that is MOS capacitor. So before studying MOSFET, which is a three terminal device, so will study MOSCAP because we want to study the behavior of capacitance. Because so for considering any device, any MOSFET or double gate MOSFET or FinFETs, the two major things which we are interested is, first is a current, how much current it can drawn, what how much current can be drawn through that device. So the more the number of current, amount of current it can draw, the more efficient the device is. So when we are talking about the current, that current is a forward current. We want as much as forward current to be flow through the device, and we want to suppress the reverse current, that is negative current, that we want as much less as it can be. So it shows the performance of our device. Second thing is capacitance. As the counterpart, we want to increase the current inside the device. Similarly, we want to decrease the capacitance of a device. So whatever the parasitics capacitance presents inside a device, this should be as low as we can make as low as possible. So the amount of capacitance inside a device is, if it's less, then the performance of device, that is delays, will be less. If delays will be less, then its operating frequency will be high. So major whatever the experiments are performed to inside a device, there are two major focuses are there. First, we want to increase the current inside the device, that is on current, and we want to reduce the off current subthreshold slope. And second part is we want to decrease the capacitance inside the device. So there are so many types of parasitics capacitance present inside a MOSFET, across drain to source terminal, source to drain terminal, gate to source. So how all the capacitance behave. So for making a general study of that capacitances, first we'll study the MOSCAP. With the study of MOSCAP, we'll study the behavior of capacitance. And once we know that this way the capacitance behaves, then there are cumulative capacitances. We'll study in MOSCAP, we'll study only one capacitor. And this type of many capacitances are present inside a MOSFET. So it will be a cumulative sum of all the capacitances. So in this way, we'll go further. So the assignment 2, that is second assignment, I'll float within today or tomorrow. The first assignment is of 3 marks. As you have seen that the first assignment is of 3 marks. Second assignment will be of 7 marks. So it will consider half portion of diode and half the complete portion of MOS capacitor. So it will be of 7 marks. Again, the third assignment will be after the midsem. Whenever the midsem get first, that is EC2 component will get over, then after that I'll post the third assignment. This will be your final assignment, lab assignment. And after the third assignment, in somewhere August or last July, you'll have the situated learning assignment. That will be your fourth assignment you can consider. So out of these 4 assignments, you will having 20 marks. There will be 20 marks. Remaining 10 marks are assigned to quiz 1 and quiz 1. That will be floated by Snehalata madam. So before wasting much more time, I'll just start where I left in the last class. Any doubt regarding that? So hope everybody has submitted the assignment number 1. Those who are left, please submit it before the deadlines. Just share the screen now. So I'll just open that flow chart, basic flow chart. So this was the flow chart, how we'll go through our experiments. So either I told you for first to make your device, then you do the simulation inside that device. After simulation, you will visualize the results. So in the first lab, I have told you how to write a script, for a device. So whenever you write a script, it will be saved in the format of .scm. That will be saved in the form of scm. Second, if you construct a device, that device you can save in the form of .set. That device you can save in the form of .set. So the output of both should be mesh.tdr file. Output of both the cases will be mesh.tdr file. So this mesh.tdr file is input to the CMD file, which is a simulation file. Once you simulate this CMD file, you will get in the form of output, there will be many files, but there will be two important files, that is design.plt and second is design.tdr. So you have already seen what is design.plt. It will give you IV or CV relations. So what is IV relations and CV relations? I'll tell you. First, when I discuss in the MOSCAP, so these two relations we'll see, that is TC relation and AC relations. This IV, current versus voltage relations, you have already plotted for the diode. Similarly, design.tdr will give you the these device specifications, how the energy band diagram of a device behaves, how the Fermi energy potential behaves, how the electrostatic potential behaves, how the carrier potential changes, electron concentration, hole concentration. All this you will see inside the design.tdr file. So today we will discuss this design.tdr file for the PN junction diode. So this is the basic flow chart. So I'll just open the lab, connect. So activities, files, this TCAT folder. In the first experiment, I told you how to copy this TCAT folder. So if it is there, you can just open this folder. So diode, TCAT. I'll just work inside this TCAT folder only. So I'll just how to construct a device. For that, I'll just show you the specification of a diode. This SCM file you have already written. So what we want, the size of P region is 250 nanometers. Size of N region is 250 nanometers. The total device size is 500 nanometers. The contacts are 10 nanometers. The size of contacts are 10 nanometers and the width of device is 20 nanometers all across the device. So I want the device like that. There are two contacts, P contact and N contacts. Then that is doping is e to the power 18. These are the meshing strategies. You can have two meshing strategies. One is that whole rectangle, which will cover the whole device, and there can be the multi-box structure also that will cover the main part of the device where the most of the operations are taking place. So we have to construct the device like that. So for that, I'll just create a folder, new folder. I'll just give a name, diode diode 1. Create. So first of all, I need the setup file. Before setup file, it will not be possible to open the tool. So I'll just copy this setup file, and also in the future I will be needing this CMD file also. I will be needing this CMD file also. So I'll copy this also. I'll just copy both. Go to diode 1, and paste it here. So these two files I have copied. That CMD file which I'll need in the later part of the experiment, and this is setup file which is necessary for evoking the tool. So I'll just right click, open in terminal, tcsh.enter, source setup.tcsh, then SDE. So this is my GUI of synchronous structure editor. Here I have to construct the device. So there, if you can see this side, there are axes, x minus y, y minus x, xy, x minus y, xz, yz. So according to your coordinates, whatever the coordinates you have defined, you can name that coordinates. So either if you are starting from minus 1.5, like in the script file, we started from minus 1.5 for x-axis from minus 1.5, that is minus 1.5, that is we are starting from minus x, and in the y we were going from 0 to 20, 0 to 20, that was positive. So the axis was, if I consider the script axis, whatever the script we have written, if I construct the device according to that script, then my axis will be x minus xy, because my x is starting from minus 1.5, that is a negative axis, that is minus x. But my y is going from 0 to 20, that is positive axis, so y is positive. That means if I exactly replicate that device, then the axis which I have to choose will be minus x, y. Then the axis which I have to choose is minus x, y. In case I start from 0, instead of minus 1.5, I start from 0, 0. Then the axis will be xy, positive xy. Again, if I'll make x positive and y negative, if I make x positive and y negative, then my axis will be x minus y. So that depends upon the how I am constructing my device. So these are axes. Again, if now in the diode there is only silicon and aluminum, we are using only two materials, that is silicon and aluminum. So for selecting the material, these are the drop down list. From here we can select different types of material. Whatever the material we are using in our device, we can choose that material from this drop down list. So before starting the experiment, I'll just first you have to go to view. You have to just go to view. In that view, the GUI mode is already by default it is 3D mode. By default it is 3D mode. So you have to make, since our device is 2D, so we have to make it 2D. We'll make it 2D. It is a 2D. Again, for diode, the first of all, we are having silicon. We are having silicon. So the material I will keep it as it is silicon. Again, I want to name my regions by myself. I don't want that should be auto named. Auto named means they will give the names to the region by themselves. So we don't want that. We want the regions to be named by ourselves. So we go to draw. Here, auto region naming I'll disable, and I will choose exact coordinates. I'll choose the exact coordinates. So now the size of my device is a rectangle. Am I audible? My voice is coming? Yes. Okay. So, from here, since my device size is rectangle, I'll just select the rectangle from here. And first I'll draw the rectangle anywhere inside this screen. So I'll just draw a rectangle here by scrolling the mouse. Now there are four regions on my device. If I'll consider the SCM file, there were four regions. Two were of silicon and two were contacts. At the last, the contacts were of aluminum. So first I'll define my silicon region. So there were two silicon regions. First was N region and second was P region. N region and P region. So the length of my N region, if I'll start from 0, let us assume that I am starting from 0. So I'll start from 0 and my length of n region is 250 nanometers. So this scale is micrometer. This scale is micrometer. For example, if I'll write here 1, then it shows that the total distance is 1 micrometer. It is starting from 0 and it is going to 1. That is the length is total 1 micrometer. Again, I am starting from 0 and I am going to 1. That is, I am going in the positive x direction. That means my coordinates will be x will be positive. But since it is 250 nanometers, so I'll make it 0.250. That is 250 nanometers. Again, y-axis, let us assume I am taking the xy coordinates, so it is 0 and the width of my device all across the device is 20 nanometers, so I'll just make it 20. 0.020, that means 20. I'll just press OK. I'll give the region name N. I'll give the region name M. OK. Now I want the axis to be xy. So there are many axes, x minus y, xy, x minus y. Since I am choosing the xy axis, so I'll just select xy from here. So it is xy. This is y and this is x. I have described my n region. I have described my n region. Now I want to describe my p region. So what I'll do? I'll again make a rectangle. You can make the rectangle anywhere inside that window. So I'll just make a rectangle here. Again, my P region will start where my N region will end. So it will start from 250 and it will go to 0.5. It will go to 0.5, 500. And the width is constant, that is from 000 to 0.020, 0.020. Again, okay. This region is P. Okay. So in this way, I have made the P region and N region. I have described my two regions, that is P and E. Now I want to put aluminum of 10 nanometers. If you can see this in the SCM file, I have contacts of 10 nanometers, aluminum metal of 10 nanometers on both the sides. These are optional. If you want to put contact directly on your device, you can put the contact directly. But if you want to put some metal before, you don't want to put contact directly on your silicon and you want some metal between contacts and silicon, so you can put that. So we'll do that. So for that, instead of silicon, since it is aluminum, I have to select aluminum from here. Aluminum. And these things you have to see now. Contacts are on the end. Side. So if you see here, this point is 0.5, micrometer or 500 nanometers. And I want my contacts to be aluminum to be 10 nanometers after where my P region is ending and 10 nanometers before my N region is starting. So what I'll do, again, I'll make a rectangle anywhere. So first of all, I define the context where my P region is ending. So my P region is ending at 500 and the contact width should be 10 nanometers. So it should be 510. Now width is almost constant, same as the N region and P region, that is 0.0 to 0.020. So I'll press OK and give name on 1, con P, anything I can give on P. Okay. So you can see this, it is now aluminum is metal is placed here. Now here you have to just imagine the coordinate system. Here, if you can imagine this, then you can draw the any device. Now I have started from 0. In the x-axis, here I have started from 0. That means 10 nanometers before x will be minus 10. It will be minus 0.010 because starting point is 0. So I want to go 10 nanometers before my starting point. So since the x starting point is 0, so for placing contact, now you can see, I'll just draw a rectangle anywhere. It will be from minus 0.010 because it is before my starting point and it will end to 0.0. In the y direction, again 0 to 0.020. Okay. I'll give contour. Okay. So you can see this, the aluminum has been placed here. Now this is, if I'll compare it with the SCM file, I have defined all my four regions, I can open the SCM file to show you. Later word I'll show you because I can compare it there. So now I want to place the contacts. So for placing the contacts, you have to go to contacts, set contact, contact sets, and you have to give the contact name. So I'll give the contact name as P side, set, and N side. P side and N side. So the P side color was there, you have seen in the SCM file. I have to select the RGB color. So it was 100. For N side, I'll just change the color to 110 and set. So I have set my two contacts, that is P contact and N contact. Now I want to place it. For that, you have to go to this pointer, just select this pointer, and from this select body to you have to make it select edge. Instead of select body, you have to make select edge. Now first I'll place the P contact. So I'll just select P side. I have to activate it. I will activate my contact, and wherever I want to place the P contact, I'll just click there. So once I click here, it will turn orange. If it turns orange, that means contact has been activated. It has been activated. It is not yet placed. It is yet not placed, but it is activated. Now again for placing it, I'll go to contact, and here I will just select set contact. Now it will change to the color, whatever the color I have selected in the RGB, it changed to that color. Similarly, I have to place end contact. I'll select end side. I'll just activate it. I'll just click. It turns orange. That means it is activated. Again, I go to contact. I'll place set contact. Now my end contact is also placed. Now I'll close it. I want to show you through SCM file. I'll just open that SCM file. So here, what I have done, I have just defined all my four regions, two of aluminum, two of silicon. I have defined my contact, P side contact, N side contact. I have given the color also. I have placed that contacts. Right at the end, right at the edge. Up to this portion, I have completed. Now next part is I have to dope my P region and N region. For P region, I have to dope with boron. For P region, I have to dope with boron, and N region, I have to dope with phosphorus. That is e to the power 18. So I'll again go to structure. Now doping. For doping, I'll go to device. In device, I have to select constant profile placement. So there are four regions in my device, out of which I have to dope two regions. So if you select here in the region, it will show all the four regions. This is region N, this is region P, this is contact region P, this is contact region 2. Out of this, I have to just dope N region and P region. So first I will dope N region. I'll select N region. I'll just make it N, and here also I'll make it N. Now for doping N region, I have to use phosphorus. So from the drop down list, I'll select the phosphorus activate concentration. Again, the value of concentration, that is, it should be 1E18. So I'll just type 1E18. And I'll just say add placement. Add placement. So that means the contacts, this region has been doped with phosphorus. Similarly, I want to dope P region. What I'll do, I'll just select P. This P region is selected. I'll make it P. Now P region has to be doped with boron. P region has to be doped with boron, and with the active concentration 1E18, I'll just add placement. Now my P region is also doped. My P region is also doped. So I'll just close this. Now I will close it. That means doping is also done. Doping is also done. Now the last part is I want to create the mesh. I want to create the mesh. So meshing strategies, as I told you, for meshing, I have to just select a rectangle which is slightly bigger than our device. So what I'll do, I'll go to mesh. In mesh, I'll select the define referral window. It should be rectangle. And I draw a rectangle such that it should cover my device. It should cover my device. I'll press OK. OK. So it is selected. Now, if you see this, I have to give the fine, how fine my mesh should be. That is fine mesh refinement of the mesh. So for that, I'll go to again mesh. In mesh, I'll go to refinement placement. Refinement placement. So since there are, I want only one. I don't want multi-box here. So this is only one referral window what I have done. So I'll just select it. And what should be there? I have given, I'll show you in the SCM file. There should be some maximum size and minimum size for that. So I'll just give the refinement size, maximum size to be 0.5, 0.05. That depends upon you, how fine you want the results. So for just demonstration, I am giving it 0.05 and minimum size 0.01. Been disconnected. Am I audible? Yes, that means voice is coming. That means only lab is disabled. So I have to just go to lab. So here I'll just give it 0.02, 0.02, 0.02. So this is my fine maximum element size and this is my minimum element size. I just create the refinement, create refinement. So that refinement has been created. I'll just close it. Now at last I have to build the mesh. I have to build the mesh. So what I'll do again, I'll go to mesh and I'll go to build mesh. So whatever the name you want to give to your mesh, because mesh.tdr file will be generated with that name. Mesh.tdr file will be generated with that name. So I'll just give name as PN diode, and I build mesh. So that means meshing has been done. Now I'll just close this. Now I have told you, if you are creating the structure, that structure will be saved in the form of .set files. That structure will be saved in the form of .set file. For that, I'll go to File. Here, Save Model. I'll make it, give it name PN diode, DIODE, and I'll just save it. So my structure has been saved with the .set file. Now I can close it. This also save. Close. This is the diode. So what is there in my folder? Initially, when I started my experiment, there was just that setup file, whatever I created, and I copied that diode.cmd, pn diode.cmd file. I copied this. So after that, these all files are generated. This pn.set, whatever I saved the structure with that name .set file. Again, the main thing what I want to tell, that mesh.tdr file, this file should be created. That means whatever the meshing we have done, it has been done, mesh.tdr file. Now I want to run the simulation. I want to run the simulation. For that, open in terminal. Tcas. First of all, I have to check what is the name of the mesh.tdr file here. That otherwise it will throw the error. So my mesh.tdr file name is pn diode. My mesh.tdr file is pn diode. What is the name here? Here name is DGT. So I have to convert it into pn diode. PNDIOD, PN diode, PNDIOD, PN diode, PNDIOD, PN diode, PNDIOD, PN diode. So these name, context name I have already given, P side and N side. These I don't want to change. Just save it. Just close it. So now I can run open in terminal TCSH roll node as device PN diode. So it ran, the simulation ran. Now I want to see the output. I want to see the output. For that, as visual. In as visual, again, go to contact, see for design.plt file. This is there. Open. P side, outer voltage x axis, P side, total current, right. So this is the PN diode current. This is the PN diode current, forward current. Similarly, if you make the voltage negative, if you make the voltage negative, it will be the reverse bias. So whatever the process we followed for writing the script, same process we followed here. Only one thing I didn't tell you, that I will tell you in the case of MOSFET, how to create the multi-box. How to create the multi-box. That is, if you want some region to be focused more, their refinement should be more fine. That we see in the SCM file for the diode. So how to create that multi-box, that I'll tell you when I demonstrate the MOSFET. So in this way, if you can follow this process also. If you want to create the structure, you can create the structure also. Any doubt regarding this? I'll just you can type it, or I'll just try to unmute you. Now, now you can ask if you want to ask something. I have disabled your
Sir, will you please explain how you did you add a concentration to those P and N side, sir?
how I added the doping concentration.
Yes, sir.
For that I have to again open that. So once you have created the structure, if you want to again open that structure, so what you do, right click, open in terminal, TCSH, SDE, enter. Here what you can do, file, open model. So it will be saved in the form of dot set. So just dot set, open. So before making any change in that device, we have to just, whatever the mesh we have created, we have to delete that mesh. So just outside device and before whatever the rectangle we created, between that just right click, and there is one option delete. So this mesh will automatically get deleted. What happened? One in terminal. Yes. Fine. One model. Thing. So this, now if you want to make any change, you can make. So for example, I want to change the doping. So what, for that I'll go to device, device, constant profile placement. Here you can see there is region, there is one option of region, where if you can see, there are 4 regions, out of which we want to dope N region and P region. So if you click here and from here, if you change the region, it will change. For example, this is N region, this is P region. So you can change the region also. For if I'll click here, this is N region. So what we have done, we have doped, just select the region. What we want to do, we want to dope it. So we have doped it with the phosphorus active concentration of 1. For example, I want to change it. I want to make it 19 or 17. I can change it 17. I can change placement. First, it will show add placement, and if we are changing, it will show the change placement. So it will change the placement. So for that, you have to just select the region, whatever the region you want to dope, you select it here. It will be highlighted here also. Whatever the region you are doping, it will be highlighted here also. Since here we are doping the N region, it is highlighted. You have to select the material with which you have to dope it and the amount of concentration you want with which you want to dope. So in this way, you can add the doping. Anything else?
Thank you, sir.
So, so this is the way you can create the device structure also. Now, in the later part of experiment, I will tell you how to see the device physics of a p-n junction diode.
Sir, one thing
No, sir.
I want to ask.
Ha ha ha.
Sir, that the designing, sir, we have done the manually, and for the there is pn underscore sir dot cmd file. So, sir, in that value we are going to change it. We will get there this thing predefined, or sir, it will get generated when
No,
we when
this CMD file is given by me. This is downloaded from that's in that you have to make changes. Only two
okay.
changes you have to make. First, whatever the match.tdr file you are saving, that same match.tdr should be input to the CMD file.
Okay,
Don't
sir.
change
So,
the
so
name.
designing we are doing the manually, and the rest of the things we are doing same things we
Ha,
are doing like CMD file with
SCM file
that
only.
only.
Ha, in that flowchart also I told you,
Hmm.
these two things are different. After that, everything is same. Either you
Okay,
create the device or script the device. These two things are different. After this, everything will be same.
okay, sir.
Okay. So
So,
now,
hi, sir.
yes, yes.
While creating P side and N side contacts, right? So in SEM file, we'll be giving the y-axis to make it center to the region, right? So, but in GUI mode, we never gave that means where exactly we need to place the contact. We just selected the aluminum
No,
region
because
of P side and
no,
side.
because in that we gave the region to place the contact because we have to define the way because we are writing, so it does not know where we have to want to place that contact. But in the GUI, we know where the contact is there, so that's why we directly place that contact there.
So
In the
it will
script file,
automatically take the center.
it will automatically take the center.
Okay.
So in the next part of the experiment, I'll just close this. So what I have done, whatever the first experiment you have done, I have made the 3 copies of it. So this is lab 1, exactly same, whatever is you have done. So what changes there only in the CMD file. In the first case, the P side voltage is 1 volt. P side voltage is 1 volt. That means it is in forward bias condition. This folder, the device is in forward bias condition. Similarly, if I'll open lab 1 another copy, here if you open the CMD file, it is almost 0, 0.001. That means almost 0. That means it is in equilibrium condition. We are not applying any voltage to our device. That means it is in the equilibrium condition. Similarly, if I'll open the third one, it is in the reverse bias condition. Here it is in the reverse bias condition. Rest of the things are same. So what you have to do, you have to similarly create 3 folders and run the S device. Run the S device. I have already run the S device. I have already run the S device here. But you have once you change the voltage of CMD in the CMD file, you run the S device so that design.tdr file should be generated. Design.tdr file. This file should be there. DGT design.tdr file. In my case, it is generated because what I did, what you have to do, once you change the voltages in the first experiment you have done, similarly, you have to create a two folder, one for reverse bias, one for forward bias. Similarly, you create the third folder in which you make the voltage almost 0.001, that is equilibrium voltage, and run the CMD file in all the cases. How to run CMD file, you know, just this CMD file you have to run. Once you will run it, you will get this design.tdr file and design.plt. So now we have seen design.plt file. Now we will see the design.tdr file. So what I'll do, I'll show you. This is with my device, that is the width is 20 nanometers. I have changed the width for you. So you have to continue with your device only. What are the specifications were there in your first experiment? You have to continue with that only. You have to open in the terminal. Since S device is already run, so I don't run S device here. I'll just directly open the S visual. I'll directly open the S visual. So in the S visual, you can go to folders. Here you will find it is lab 1 copy. You have to see which folder has been opened. So it is opened lab 1 copy. So in lab 1 copy, you have to open the design.tdr file. You have to open the design.tdr file. This is design.tdr file. Just open it. So it will open your device. It will open your device. Now you want to see inside your device. Now you want to see inside your device. So if you can see, this is y-axis and this is x-axis. If you can see, this is x-axis and this is y-axis. In x-axis, our device is 500 nanometers. 500 nanometers. And in y-axis, it is 20 nanometers. It is 20 nanometers. So to see inside the device, I want to cut it exactly into half with respect to x-axis. I want to cut my device exactly into half to see the device physics. So I have to create a cut such that it divides my device with respect to x-axis into two halves. So for that, I'll create a cut. If you can see this y-axis, it is exactly at the center. If my device size is 20 nanometers, so it will be exactly at the center. So for that, I have to just go to precision cut. Here is the option of precision cut. I'll just select it. Here you have to select the free line cut. So in the y-axis, in the both initially by default it will show half. It will show exactly at the center. Starting point it will show exactly at the center. If you can see in the y-axis it is 0.02. My device size is 0.02. That is 20 nanometers. That means it is showing exactly at the center, that is 0.01. So we want it the cut line to in with respect to y-axis exactly at the center. We want the cut to be exactly at the center. So this we will not change. Y-axis we will not change. In the x-axis, the line should be all across the device. The line should be all across the device. So what I'll do, I'll change the x-axis. My device is from 1.5 to 1. My device is from 1.5 to 1. So what I'll do, I'll make it 1.5 and this I'll make it 1 because in the X I want it create line which creates it all through the device. In the y-axis it should be exactly at the center. Once I'll create the cut, so you can see this, it has created one cut all through the x-axis, but y-axis it is exactly at the center. So this is the cut for lab 1. Lab 1, copy lab 1 is reverse bias condition. Copy lab 1 is the reverse bias condition. This is the reverse bias condition. You name it reverse bias, forward bias. Now what you can do, once this cut is created, you have to just select this and here you will see the band diagram. Here you will see the band diagram, plot band diagram. You just click on the band diagram. So I'll just show you this afterwards because it will remove everything. So this is the band diagram. This is the band diagram in the reverse bias condition. This is the band diagram in the reverse bias condition. Similarly, what you can do, you can plot the band diagram in the forward bias condition and in the equilibrium condition. You have to plot three band diagrams, one in the reverse bias condition, one in the forward bias condition, and one in the equilibrium condition. And after plotting all the band diagrams, you will see some difference in all the three band diagrams. There will be slight difference in all the three band diagrams. So you have to write just two lines for each case. Why the bands are near in the P region, in the reverse bias, why band are separated, like that you have to write two to three lines for describing the band diagrams. Similarly, I'll just select this. Here, if you can see, there are so many things you can see with respect to device. There are, you can plot absolute electric field, acceptor concentration, band to band barrier potential, doping concentration, so many things are there. So you can explore all this if you want to explore. So first, for the lab experiment, you have to plot the band diagrams for all the three cases. Now in the second case, what you have to do, I have already only opened one device here. I have already opened one device here. I'll open all the three devices here similarly. So what I'll do, again, I go to folders. In folders, here is one option to go back, to go to the parent directory. So once I'll go to parent directly, here I have opened lab copy one. I have opened the lab copy one. Now I will open the lab one. Here also I will search for design.tdr file. So here is design.tdr file. I'll open it. So this is design 2 is for the lab. This is forward bias condition. This is forward bias condition. So again, I'll select it, precision cut, same cut line. It will from minus 1.5 and to 1.0. Create cut. So it has created the cut. Similarly, I will open the third file, that is another copy.
It is
Again,
applied in the forward bias.
I'll just afterwards you can ask the questions. I'll just describe. Now this is lab 1 was a forward bias. This lab 1 copy was a reverse bias. Now this another copy is the equilibrium condition. I'll open this also. Again, design.tdr file open. So this is equilibrium condition. I'll open it. Again, create a precision cut. It will be minus 1.5 and it will be 1.0. Create cut. Now I have created all the three cuts. I have created all the three cuts. So I'll just select here and I want to plot the absolute electric field for all three cases in the same graph, so that I can compare the absolute electric field. So what I'll do, I'll just select the absolute electric field. So it has plotted the absolute electric field. So for making it zoom, you just select it and here is one option, maximize. You just click here. So it will maximize whatever you want to maximize. So these are the three different graphs. These are the three different graph of absolute electric field for the three different cases. So what you have to do, you have to just compare. You have to just compare why for the forward bias condition it is the absolute electric field is very less. For the reverse bias it is maximum, and for the equilibrium condition it is between forward. These reasons you have to write why it is like that. So this absolute electric field you plot and you write the reasons why it is like that. You plot the band diagram, you write this. So this will be the first part of your experiment number 2, assignment number 2. This will be the first part of your assignment number 2. Similarly, you have to plot the barrier potential. You have to plot the barrier potential. From here, you can see the barrier potential and you can plot it. So one thing which you have to keep in mind, whenever you are creating cut, for example, I'll just create cut once again to show you. For again, zoom in, you just click here again, it will again, and whatever which is zoom, it will again become small. So for creating cut, what I want to tell you, since my device size is 1.5 and 1, it is going 500 nanometers, which is starting from 1.5 and going to -1. but your device size will be different. So you make the cut accordingly, whatever the starting point of your device and in the x-axis and what is the end point of your device in the x-axis. This is for x-axis, and y-axis, this is 1 nanometer, 10 nanometers, because my whole width of my device is 20 nanometers. For your case, the device width is somewhat different. So that this will automatically, by default, it will come at the center. So this you don't change. Y-axis you don't change. X-axis, keep in mind whatever the maximum size of your device. Before, do not include the context. Do not include the context before including the context. What is the size of your device? Make the cut accordingly. Again, for selecting a particular window, just click here, that window, it will be selected. For zooming it, here is the option, just click here, it will maximize. Again, click there, it will minimize. So in this way, you can plot and see the device physics inside any device.
So what is this Persian cut? Like it plots in that region or?
This is, for example, we want to see what is happening inside our device. What is physics? What is the physics going inside our device? So we can create cut anywhere in the device. So it will plot, it will give the device physics according to that portion of our device. So generally we want it should be exactly at the center, so that we can see what is happening inside exactly at the center in our device. That's why we have created the cut, to look into the inside our device.
Okay. So it plots in that line of region.
For our device is 2D, so it has cut exactly at our device like that. It has become two halves. It has become the two halves, first upper half and lower half, and we are at the center of that, and we are seeing all the physics happening there.
Yeah. Okay. Okay, sir. Yeah. Got it. Thank you.
So this will be your first part of the experiment. You just do it. In the later, now we will come to the second part of the experiment. I am completing the third. Usually this mouse cap I'll take in the third lab, but I want to tell you as much as I can tell you about the tool. That's why I want to cover the mouse cap also today, and it will cover most of your assignments. Before mid-sep, I want to cover most of your assignment. Almost 10 numbers will be covered, so that after mid-sem it will not be very high. Burden for you to cover the assignment. So the second assignment will be of 7 marks. So first portion I have told you what you have to do. In the second part, it will be the mouse cap. It will be the mouse cap. So I'll just show you what a mouse cap look likes. So this is the mouse cap. That is metal, oxide, and semiconductor. Metal, oxide, and semiconductor. So why we are studying it? Again, I told you we want to study the behavior of capacitance, how a capacitance behaves inside a device. So there are so many capacitances where whenever oxide is separate, whenever you separate any two semiconductor or two metals plates with oxide, some capacitance will be formed, some capacitance will be formed. So for uh, for any device, these capacitance are not good. These are parasitics for that device. So if this amount of capacitance is more inside the device, it will have more larger number of delays. So how a basic capacitance inside a device look like? So this is a metal, this is a semiconductor, and it is separated by a thin oxide layer. So this will result in some capacitance inside the device. So we'll study how it behaves. So in the theoretically, madam will tell you in the class how the capacitance behaves, parasitics capacitance, but I'll just give you a brief introduction of how it behaves. So for constructing a device, please remember whatever the size I have taken, the width, or you can say that x-axis, it is 100 nanometers. In x-axis, it is 100 nanometers. In the y-axis, or it is 250 nanometers is the silicon, that is semiconductor. 5 nanometers is oxide, 5 nanometers is oxide, and 20 nanometers is the aluminum. 20 nanometers is the aluminum. two contacts will be there. Above contacts we term is gate, we will give the name as gate, and the lower contacts is as body. The lower contact is body. Again, what is the how a capacitance inside a device behaves? So I just give you a brief idea about that. So I try to make something. So it goes through three regions of operation. What you normally do, you apply voltage to the gate. You apply voltage to the gate. When you apply the voltage to the gate, your device behavior starts changing. Your device behaves start changing. First, initially, when the voltage is very less, hardly any change is there. Charges accumulate on the boundary, on the channel regions. Once the applied voltage increase, so the second region will come, that is depletion regions. Charges start to deplete by the ions. Ions takes place the place of charge. Wherever the charges are there, it get depleted, and the charges are now that place has been taken by the depletion ions, that is unmovable ions, they can't move. And when again you increase the voltage, inversion take place. That means if the device is p type, the whole body is p type, there will be a small n channel. And if it is n type, whole body is n type, there will be small p channel. So that is called inversion. So our device usually operates in three regions. So when these three regions, capacitance also changes. So if you can see this, first, since there is metal and semiconductor separated by the oxide, so there will be only one capacitance, that is Cox, oxide capacitances, which is Cox, which is given by Eox by epsilon ox by Tox. That is, Tox is thickness, what is the thickness of oxide, and Eox is the epsilon value, E0 E plus ER, that you know. So this will be that value. Again you increase the voltage, that is, you are increasing the gate voltage. What will happen? There will, since the depletion charges will come to the boundary, this is the semiconductor oxide boundary. So the ions will start accumulating here. So it will result to for the formation of one more capacitance, that is depletion capacitance. So there will be two capacitances in the series, that is oxide capacitance and depletion capacitance, that is Cox bar plus depletion capacitance. So as we know, the series combination of two capacitance will decrease the value of capacitance. That is, it will become 1 over Cox plus 1 by C depletion. So the resultant capacitance of addition of these two capacitance will result in the small value of capacitance. So you can see here the capacitance value is decreasing. Now again, you increase the voltage. So this immovable ions will be removed, and there will be a inversion layer will be formed. So this depletion capacitance will not be present anymore there. So again our capacitance will come into the whatever the original value is there, that is C oxide capacitance. So this is low frequency. When you are operating your device in a low frequency, it will again return to the inversion region. But when you are operating your device in the high frequency zone, instead of going to the inversion layer, it will be there in the depletion region only. So the capacitance will be, the value will be Cox plus C dep. So in the why it is happening, just you have to write 2 points for that. Why in the high frequency your capacitance is C value has less value, and in the low frequency operation why the value is high. So this comparison you have to just in the 3 to 4 lines you have to just describe it, why it is behaving like this. So this is a basic operation of capacitances, how capacitance behave inside a device. Again, there are two operations of a device. DC operation and AC operation. If DC operation, in DC operation, Mainly we are considering the current. Mainly we are considering the current. We look for IV plots. We look for IV plots. Similarly, if we want the AC operations of our device, we look for the capacitance. We look for the capacitance. So normally the CMD file, whatever the simulation file we use, for DC simulation the file is different, and for AC simulation the file is different, because the resultant for both the cases are different. CMD file for AC simulation will give you current and capacitance both. You can get both. If you want, you can get both. In the AC CMD file, you will get the capacitance also and current also. But if you are running the DC CMD file, if you are running only DC CMD file, the resultant will be only the current. The resultant will be the current, because there will not be any phenomena of capacitances. To be clear, I'll just show you the graph also. That so this simulation CMD file are basically of two types: AC CMD file, PN junction diode AC.cmd and DC.cmd. Major difference between both the CMD files are that if you are doing the AC CMD file, you are performing the AC and DC simulations. The output will be IV and CV relation. The output will be IV and CV relation. But if it is only DC CMD file, it is only DC CMD file, you will get only the IV relation, that is the current relations. So this is how MOSCAP operates. More detailed about the MOSCAP you will study in the class, theoretical class. So as I told you in the initial class also, first class also, if you have only one CMD file, if you are having only one CMD file, SCM file, and you want to convert it into another SCM file. So let us say we have a SCM file of diode only. We have the SCM file of a diode only, and we want to convert the SCM file of diode into a SCM file of MOSFET. So we can do that. We can do that. Also, if we have the CMD file of MOSFET diode or MOSCAP, we can convert it into the MOSFET, double gate MOSFET, any file. So I'll tell you, I'll show you how to convert it. So for that, I again go to the tool. MOSFET. So I'll just create a folder here. New folder. MOSCAP. MOSCAP. DEN MOSCAP. Create. I have created a folder. Now I don't have any files. I don't have the SCM file. I don't have the CMD file. So what we can do, we can convert the diode SCM file into the MOSFET SCM file. So what I'll do, I'll just copy the diode SCM file. I need this also. I'll copy this also. Copy. I'll just paste it here. I'll just paste it here. Paste. So if I open this is a diode SCM file. This is a diode SCM file. So if I'll open my MOSFET structure, it has basically, for my diode, there were 4 regions. It has only 3 regions: aluminum, oxide, and silicon. Aluminum, oxide, and silicon. First region is aluminum, second region is oxide, third region is aluminum. So what I'll do, so the width of my aluminum is 100 nanometer. Here it is 100 nanometers, and here it is 20 nanometers. So what I'll do, I'll just, since here there are 4 regions, so first of all I'll delete one region. This I don't need. So what I'll do, I'll just delete it. Delete. So first region is aluminum. First region is aluminum. I'll just copy aluminum. paste. Last region is silicon. Last region is silicon. I'll do that. Paste. So first region is aluminum. Again, I start with minus 1.5. So first region is aluminum. Is y direction, in x direction, let us consider it is 20 nanometers. It is 20 nanometers. So 1.5, 20 nanometers, if I'll come down, it is 480, 480. And that it is 100 instead of 20, now it is 100. Instead of 20, now it is 100. So I'll make it 0.100. So this is my aluminum. I have defined my first region. This is aluminum. Region 1, aluminum. Region 2 is, I'll give the name also because it is not P side, it is metal. I'll just give the name metal, METAL, metal. Similarly, my second region is oxide. It is not silicon, so I'll just make it oxide. Oxide. Now, thickness of oxide is only 5 nanometers. Thickness of oxide is only 5 nanometers. So my metal is ending at 480. My metal is ending at 480. So my oxide will start at 480 and it will end at 475. 475. It will end at 475. Again, thickness is fine. 100 nanometers. 100 nanometers. Now my third region is again silicon. So silicon, where my metal oxide is ending, 475, and it is 250. So 475 minus 250 will be 225. 225. Again, it is same 100. So this is the what is it? Silicon. RAGIO region. Shift underscore 3. So this is my region 3, that is silicon. Now contacts are not P side N side. It is VAT gate and body. Shift BO body. Color I don't want to change. Color should be as it is. So now positioning. Now positioning will change. Positioning will change. Now my gate contact will be exactly on the aluminum, where my aluminum is there. So it in the x-axis it is 1.500. Now I want to place it at the center. Similarly, as I did in the diode I placed, because the contacts was on the sides, left side and right side. Now it is at the top. It is at the top. So top, it is exactly at the center. That means the total thickness of my device is 100 nanometers. So center will be 50. Center will be 50. So it will be minus 1.500 to 50. Contact name is gate. Shift GATE, gate. Similarly, second contact is body. Exactly, it will be placed downside where my device is ending. It is minus 1.225. And that too at the center. So if I'll show you the device, this is my contact at the top and this is at the bottom. This is width exactly at the center, exactly at the center. So now next, there is only one doping. We don't want to dope both. There are no, we have to only dope one region, that is silicon. There is only region 3 which we want to dope. So I'll delete one doping. Delete. So it is body, what, not P side, end side, BODY body. And what is the doping profile is the boron active concentration, and I'll just dope it with e to the power 17. Whatever you want to give, you can give. Now this is region 3. This is not region 1. This is region 3. Now comes the main part, that is creating a rectangle which should cover my whole device, which should cover my whole device. So if you can see, minus 1.5, it is starting from minus 1.5. That means any point above minus 1.5, that is minus 1.510 will do. And it is ending at minus 1.225. So any point below minus 1.225, that is minus 1.220 will do, 22122, any point 220, 150, 1.50, any point below that will do. Similarly, in the y case, it is from 0 to 100, 0 to 100. Any point below 0, that is 0.0 minus any minus point, 0 minus 0.010, minus 0.20, any point negative will do. And 100, any point greater than 100. So greater than 100 will be 110 will do, 120 will do, 130 will do. So this is right. Here we don't want to change because minus 510 is just about 100. Here it's, this will also do. This will also do because it is, we are starting from 0 and it is 0 minus 0.020. That is above my 0 point. Here we have to change. Now my device is ending at minus 1.225, minus 1.225. So here it will be any point, minus 1.20200. So this point is 225. After 225, minus 1.200 will come. This is fine. Again, 100 nanometers is my width. 100 nanometers is my width. So any point greater than 100. So 120 will do, 120. So this is done. This is meshing. Again, I tell you, I want to create a rectangle such that it should cover my whole device. So here it is starting from minus 1.500. So minus 1.510 is above that. Last point is minus 1.225. So minus 1.220200 is below that. So the x-axis is covered. Y-axis, it is starting from 0.000 to any negative point to 0.020 minus 0.020. It is negative. So it will cover the top portion. And 120 will cover the bottom portion. So I have made it like that. You can give any point like this. If you give minus 0.030, it will do, minus 0.010, it will do, but it should be greater than 0.0. It should be, well, greater means it will be more negative to 0.0. Here, since it is 100, it is going from 0 to 100. So any point after 100, so it is 120, it will do. Now this is the meshing refinement meshing. Now multi-box, if I want some portion where the meshing will be more fine, what is that region? If you just draw minus 1.450000 to minus 1.5020, that point is exactly at the center, a thin line exactly at the center. 1.450, that means minus 1.5, say 50 nanometers down, and 000 means it is right corner and it is going to 20 nanometers. That means 20 nanometers. So you can draw in the, if you draw in the pen and paper, you will find where this multi-box concept is there. So here we have made the refinement fine. You can, I have given the DGT name only. You can give any name. You can give any name. You can give MOSCAP name, any name to save it. Once I'll save it, so it will become the MOSCAP. So what you have to do now, you can see I have already done final MOS. So there are three different regions. Silicon, dielectric, that is oxide, and metal. There is three regions: silicon, dielectric, and metal. So M1, M2, M3 represents three different metals. M1, M2, M3. I have made the folder. This represents the three different metals. Three different metals means you can use any three metals. You can use any three metals. So right now, if you can see this, M1 I have placed metal, M2 here also aluminum, M3 here also aluminum. Why have the what is there? I have placed aluminum all there, but what I am telling, we should change the metal. So instead of what I did, instead of changing the metal, what I did, what is the change in, if I change the metal, its work function changes. It work function changes. If the work function for aluminum is something 4.50, and if for other metal, for example silver, it will be 11.7, something like that. So only difference between two metal is their work function. If you change the work function of a metal, work function is different, that means that metal is different. So instead of for demonstrating, instead of going for new metals, what I did, I have changed the work function of aluminum itself. So when I change the work function of aluminum, it behaves like some other metal. So in what I did in all M1, M2, M3, I have changed the work function of metal, and since I have changed the work function of metal, it is behaving like different metal. Similarly, D1, D2, D3, the dielectric value, E value, epsilon R, epsilon 0, that ER value is different for different dielectrics. So here we have used the SiO2, silicon dioxide we have used. But if I change the dielectric value of silicon dioxide, is some 11.7, I think is the value for silicon. If I change this to some other value, it will behave like some other dielectric. So here also I have done that, like that I have changed the dielectric, so it will behave like three different dielectrics. So it is to just demonstrate you how you can change the dielectric material and metal to change the metal work function and dielectric value. So if I'll just open one file. So this is a CMD file for the MOSCAF. If I'll open it, so here if you can see this, I have copied one more command which was not there in the diode, that is models.parameter files. That is models.parameter file. Why I have input this files here? Because I want to I am changing the models itself. I am changing the models files. There are many different files, aluminum file, oxide file. So I am making the change in that file. I am making change in that aluminum file and oxide files. That's why I have copied that models.pr file here. If I'll not copy this models.pr file, and if I'll make the changes in the aluminum file or oxide file, it will not take that value. So for that, I have copied that models.parameter files here. Similarly, if I'll copy this file here, it should be present in my working folder. It should be present in my working folder. So if you can see this, it is present. Where is this models.pr file is present in my working folder. So whenever you are doing any change in the parameter files, that models.pr file should be there present in your working folder. So this is CMD. What is the change in the CMD file? You can see this. These all are same. I have one sentence I have copied, that models.pr file. Now contexts had been changed. Instead of body, p side and inside, contexts are gate and body, and rest is same. Rest is same. So I have not given any voltage to the gate. You can see this gate voltage is 0.01, almost zero. That means we want to just study the, we don't want to study the characteristics of a MOSFET. Here we are not studying the characteristics of MOSFET, how a capacitance behaves. Here only we are seeing how a work function of metal changes the Venn diagram of a MOSFET, how the dielectrics of a oxide changes the Venn diagram of a MOSFET. This we have to see. That's why I am not given any voltage. I am just observing this case at the equilibrium condition, and the equilibrium condition. So what you have to do, if you can see, this M1 and D1 will be same, because here I have not changed the metal work function and dielectric also. So this M1 behaves, if you can see here, both metal work function and dielectric values are same. It is identical. So this M1 and D1 folders are same only. If you open this M2 and if you open this aluminum file, so this is the parameter file of aluminum. This is the parameter file of aluminum. So what you can see, just type Control F here. If you type Control F here and type work function, WORK work, you can see work function. Here work function is 4.60. I have made the work function as 4.60. Save it, use it. M1. Similarly, I open the Control F work function. If you can see this, here work function is 4.10. Here work function is 4.10. Similarly, if I open M3, Control F, it is 5.10. So what I did, I changed the work function at three different same aluminum file, so that it behaves like three different metals. Now what I did, as you see, I run the CMD file. I run the CMD file. Why I run the CMD file? I want to see the design.tdr file. I want to see the design.tdr file. So again, what I'll do, open in terminal, ECSH. Oh, again, one thing you should note, if if setup file is not there in your working folder, if setup file is not there in your working folder, it will not open. The tool will not open. So in M3, there is no setup file. So that's why it is not open here. M1, M1 also it is not there. M2, M2 it is there. That means you can open the tool here. So just open in terminal, TCSH, source as visual, enter. Again, folders. You can here it is, here I have open M2. Here I have open M2 and I will look for design.tdr file. Design.tdr file. I'll just open it. Now again, here also I have to make the cut. Here also I have to make the cut. Same concept, y-axis along x-axis. Now in the previous diode case, I have not included the metal and SiO2. Here I'll include the whole device, that is metal and oxide. So precision cut, recut. In y direction, I will not change. In the x direction, it is from 1.5 and let us make it 1.0. create cut. It has created the cut. Now again I'll go to folders, back folder. I'll open M2. Now M2 is open. I open M1. Here I'll see for design.tdr file. Open. This is M2. Oh, M1. I have to create precision cut. Same way, reline cut. I'll not change y-axis. X-axis it will be minus 1.5 to 1.0. Create cut. Created cut. Similarly, I'll open M3. Design.tdr file. Open. Create cut. Precision cut. I'll not change the. I'll just 0. Create cut. Now I have created the cuts for all three cases. I have created the cut for all three cases. I'll select this, and here I'll plot the band diagram in the same graph. I'll plot the band diagram for all the three cases. Okay. So you can see this. There is a slight change in the band diagram for all three cases. There is a slight change in the band diagram for all the three cases. So for work function 4.0, work function 4.50, and 460 and 5.10, there is a slightly change in the work function. So you have to just plot this and write 2 lines. What is happening with the change in the work function? If we are changing the work function of metal, what is happening? So any doubt? If you have any doubt, you can ask. I have unmuted you, can ask. Now it is unmuted. You can ask.
Sir, can you explain what is work function, sir? In that EV file, you are mentioning that, sir.
Work function is particularly defines the operation of a metal. If work function changes, the properties of a metal changes. So what is the effect of work function in case of MOSFET? If you are using different metal for a in MOSFET instead of aluminum, if you are using the because the work function of aluminum is 4.10, for example, if I have replaced it with the some other metal whose work function is 4.60, then my energy band diagram has changed. So you have to just figure out why it is like that, what is happening so that the energy band diagram is shifting like this. I'll explain in the next class, but for the assignment you have to just write that key what is the reason by work function. If I'm changing the MOS in the MOS capacitor, there are three things: metal, oxide, and semiconductor. If in that case, if I'll change the different metal, the energy band diagram changes. So what happens to energy band diagram, how it changes? So work function defines the properties of metal, how it will conductivity changes, how it behaves, metal behaves.
Thank you, sir.
So again, any doubt?
Sir, you have sir like created three folders with M1, M2, M3, and sir, whenever we will run the sir HCM file, sir, it will generate the file in that aluminum TDR, sir. In that we have to change the value
No, no,
and
no.
run
I am
that.
telling you. I am telling
Okay.
you. I'll just these. Okay, these aluminiums dot when you will cancel close terminal. I'll just go to home. Control L backslash etc backslash s s k e l backslash enter. So this is your ticket folder. Whatever the ticket folder you see, this is the ticket folder. If you open this transfer folder where I am working, it is here. You can find final mouse. Here you find M1, M2, M3. You don't need to create M1, M2, M3. It is already there. You can just if you copy this folder, whatever the folder I am demonstrating, it is there only. So you have to
So
just
sir,
open.
just we need to copy and run that, and we have to find why the graph is
Huh.
changing with
The
the
only
work
change,
function.
what I can ask you to do is in the SCM file, instead of, for example, if I'll open the SCM file, instead of giving this width 100 nanometers, I can make it 150, do it for 80 nanometers or 150. This change or this change. Otherwise, nothing will change. These parameter files are already copied in that folder. You can see aluminum parameter file, oxide, models.pr file. Every file is there already inside the folder. What you have to do, you have aluminum file, for example, this also already I have changed in the M1, M2, M3. You can see this in M1, M2, M3 that change is already made. So you don't need to make that changes also. Again,
Sir, that
yes.
sir, that aluminum dot per file, sir, you have created manually, or sir,
No,
just
this is
after running SCM file, it will
no,
generate.
it is there. I have copied it from the manual. It is not generated. It is not created by me. It is there present in the whatever the user guide is there of Centerus ticket. It is present there. I have copied it from there.
Okay, sir.
Yes. So don't this M1 and D1 is same because in M1 and D1 both oxide and epsilon value and this is same. So you whatever you plot for M1 it will be plot for D1. You have to just plot for M1, M2, M3 one plot and second will be M1, D2, D3. This will be the change with respect to dielectric. So there will be two graphs. One will be M1, M2, M3. Second will be M1, D2, D3. So what I can expect you to do, if you can do, is just change the structure, device structure. Nothing you have to change. In M1, go to SCM file, make the change, but make sure whenever you make the change in the, you don't do that also. Otherwise, you try it by yourself to change the SCM file. You can change the SCM file, whatever the specifications I'll give in the question. You just make the change here. So when you change the SCM file, so what you have to do, you have to delete this, you make the change in the SCM file. So you have to just open it in the SD. Usually what we do, I'll just show you that also. Otherwise it will be, I'll just create a demo folder. So since I'm working here, that's why it's not opening. I'll go to home again, close it. For example, new folder, boss cap demo 2 1. Okay. This is the folder. So what this aluminum parameter file, where is models.par dd.cmd file, silicon oxide, and this dgt.scm. I'll copy it, final mouse, I'll paste it here. One more thing I have to copy, the tool, otherwise it will not evoke the tool. Copy, paste. Now what I did, I have copied everything here. Now what you do, you have to make the what if I make you ask you to make the change, that change will be in that SCM file. You have to make the change in that SCM file. So what you do, you just open this SCM file, make the changes, whatever the changes are there, and save it. Save it. Now, after saving it, you have to open it because there is no mesh.tdr file, nothing is there. What you to do, you have to just open it. Open in terminal, tcsh, setup dot. So file, open model, SCM file, just open it. So once you open this, now that mesh.tdr files will get generated. This mesh.tdr file get generated. Now once this mesh.tdr file gets generated, now you have to run the simulation. So as device dd-dos underscore cmd, just run it. So once you run it, now that design.tdr file got generated, this design.tdr file. So if you don't run the simulation, this design.tdr file will not get generated. If you will not open the SCM file, this mesh.tdr file will not get generated. Now you can visualize that. Enter. File. Open. Design.tdr file. Open. Again create the cut. Recut. Zero. Create cut. So this is the bend. This is respect because I have copied everything from M1. So this graph is respect to M1. This graph is respect to M1. So just be careful what you have to do. If I ask you to change the device, you just copy all the files in folder 1 and open that SCM file. Open that SCM file. Before copying before making it M1, M2, M3, please note that thing. Before making the 3 folders M1, M2, M3, first make one folder, copy all the files, make the changes in the SCM file, whatever the change I have asked you to make in the SCM file, make that change in the SCM file. Once you make the change in the SCM file, open the SCM file. Once you open the SCM file, mesh.tdr file will get generated. So once the mesh.tdr file is generated, then you make the folder as M1, M2, and M3. Got it? So what you do, first make a folder, copy all the files as I told you, copy all the files, make the changes in the SCM file according to the given question. Once you make that change in the SCM file according to question, just save it and open the SCM file in SDE. Once you open that SCM file in SDE, that mesh.tdr file will get generated. Mesh.tdr file will get generated. Now, once that mesh.tdr file get generated, before running the S device, make 3 folders M1, M2, M3. Make 3 folders M1, M2, M3. And in that 3 folders, what you have to make the changes? Either you can copy the aluminum. You have to make the change in the aluminum file. You have to make the change in the aluminum file. Here it is Control F, work function, WORK work function. Here it is 4.10. In folder number 2, that is in M2, just change the value to 4.60. Just make the value 4.60. In the third folder, make this value at 5.10. These 3 changes you have to make. So this, and run the CMD file. Run the CMD file in all 3 folders. So first option is create all the file, copy all the files, open SCM file. Again, I am telling you, open SCM file. In the SCM file, make the changes, whatever changes I told you, open that SCM file. Once you open the SCM file, then copy that folder to two more folders. Copy that folder and create two more folders. Now you will have three folders, same folder with three names. Now the three folders are identical. The three folders are identical. So before running the CMD files, before running the S device on all the three folders, just make the change in the aluminum file. M1, keep it as it is. In the M2, change the aluminum parameters to 4.60. In the M3, change the aluminum parameter to 5.10 and run the simulation. So this is the process. If you don't follow, if you know the process and if you don't want to repeat the same job again, what you do? You just copy this folder from the TCAT folder. It will be there, this final MOS. Just run the simulation here. For first graph M1, M2, M3. For the second graph M1, D1, M1, D2, D3. Don't, I'll just delete this. It will be there in your folder. So you just don't use D1. M1, M2, M3 and second M1, D2, D3. So this is the process you have to follow.
Sir, what is the change in D2 and D3?
It is dielectric values changing. Epsilon value has
Okay.
changed.
Okay.
You can see where you can change the dielectric value, it will be in the oxide. It will be in the oxide file. So here epsilon value is 3.9. D2 side. It is 10.2.
Okay.
Similarly, in D3, it will be something like. So this will be your assignment number 2. This will be your assignment number 2. Oh, second part of the assignment number 2. So any doubt?
Sir, what is there in that silicon.par?
It is the parameter file of silicon. It is the parameter file of silicon. So if you want to change the semiconductor silicon to germanium,
Okay, got
so
it.
that is there, but we are not we are not changing that. Usually I ask to plot the doping. If we change the doping of silicon, what is the effect in the Venn diagram? But assignment will be very big, so I am skip that. You can change the doping for silicon and see the variation in the output.
Okay, sir. And one more thing, how this aluminum.par, oxide.par is linked to the, like where those files are being called? Is it in CMD file? Those
It is,
files,
I told you na. I told you it is in the models.pr file. It is. I have inputted the
models.pr. Okay.
models.pr file. If you can see the CMD file, where is the CMD daily.cmd file? Here one more file I have included, parameter file, that is models.tr file. So all the models files, whatever the model parameter files are there, those are all included in this models.par file.
Okay, sir. Yeah, I got it. Thanks.
Okay, so I'll most probably by Wednesday or Thursday, I'll upload the assignment number 2. And before your midsem, you just submit that. So after midsem, we'll go for MOSFET, then double gate MOSFET, then we'll see the synchronous workbench tool, and then the last lab, I'll just show you the 3D FinFET, how to construct a FinFET, 3D FinFET. So that's all from my side. If you have any doubt, again, you can contact me through MS Teams messages. Just stop sharing. One more thing I want to tell you just before ending the lab. Files. I have created the structure also. For example, if you don't want to write the script of MOSFET, you can create the structure also. I have created it somewhere. Here it is, dot set. Open in terminal. PCSH LGA SD. So this is the structure I have created. This is the structure I have created. Similarly, if you want to create much more clear. So this is the structure I have created. What I did, first I took the silicon. Here it is 100 nanometers. Here it is 100 nanometers, and here it is 250 nanometers. So I just created that region 1. Then I changed the material from here to silicon to oxide. I changed the material from silicon to oxide, and same length is 100. This is 100 nanometers, and this length is 5 nanometers. I made it like that. In the third case, I select the metal from here, aluminium, and I gave the coordinates as 100 nanometers plus 20 nanometers, since its width is 20 nan. Then I place two contacts. This is gate contact, and this is body contact. Then there is only one region to be doped. This is that region. If you can see this constant profile placement, I will show you device constant profile placement. So there are three regions. Out of that, only substrate, that is body, to be doped. So there are oxide, no need of doping, metal, no need of doping, only substrate we need to dope. So I'll just select it substrate, and I doped it with boron, electric concentration of e to the power 17. Then similarly, I made the box like this. So what I did, I made a rectangle around it, and I just run the meshing. So if you want to create, you can create the structure also. So that's all from my side. I'll